And when we make reference to density, density is a proportionality. You guys know what I mean when something is proportional?
Yes.
Okay. So can you give me an example?
Someone's weight to their height.
Someone's weight to their height. Okay. So yeah, proportional. So in a sense that if they continue along that route, then their weight to their height is always going to be proportional. Like let's say a little kid growing up, and their height is proportional to their weight. So then in the theory, as their weight increases, their height should increase. Is that correct?
Yes.
Okay. So since that's the case, often we will write a proportionality, and I'm going to use your example. So we'll use mass is proportional to height. Okay, so does it say that the mass is equal to the height? Are we saying that?
No.
No, we're just saying it's proportional. So as that kid gets taller, that kid's going to weigh more. Okay, so that's what we're saying. Okay, so in chemistry, we often will run into proportionalities, right? We can say temperature is proportional to pressure. Okay, so let's say we start boiling water, right? And let's say we put in a container like this, and we were boiling the water in here magically without melting our plastic. Okay, so what's going to happen over time?
It's going to evaporate.
The water's going to evaporate, and if I have my lid on, what's going to happen?
It's going to fill up if you keep adding water.
Not keep adding water, but if I keep adding temperature, if I keep heating it up, what's going to happen to the water bottle?
The pressure is going to increase.
The pressure is going to increase, right? And then eventually it's going to increase so much that it blows up the bottle. Okay? Are you guys kind of clear on that one?
Yeah.
Yeah. Okay. So I'm not saying that temperature equals pressure. I'm just saying that they're both increasing. So that's a proportionality. Okay. So, but with proportionality, if we provide a constant, I could sit there and make temperature equal to pressure. Okay, so if I use a constant, K here is going to represent my constant, then I could sit there and make temperature equal to pressure. Okay, and a constant is just that, it's constant. Okay, so there's two ways of looking at proportionality. One is you have directly proportional, meaning that both quantities are going up, so that both quantities are increasing. And then the other one would be indirectly proportional, where one is going up and the other one is going down. Okay, do you guys get that? So we have directly and indirectly. Okay, you guys, are we clear?
Yeah.
Yes.
Okay.
Yes.
So the proportionality that we're going to start off with is mass and volume. So if I have, let's say the mass of my liquid can be proportional to the volume of my liquid. Okay, so I'm going to ask you a question. So if I have a 16-ounce bottle of water, and I have a liter of water, okay? 16 ounces is my volume. 16 ounces is approximately 500 milliliters, okay? Or the 16.9 fluid ounces is about 500 milliliters, okay? So 500 milliliters of water or a liter of water, okay? Which one is going to weigh more?
The liter.
The liter. So as my volume goes up, my mass goes up. Okay, I'm going to ask you another question. If I have a liter of water or a gallon of water, which is about 3.785411 something liters, which one is going to weigh more, a liter or a gallon?
The gallon.
Gallon. Okay, so that's proportional, right? The mass is proportional to the volume. As the mass goes up, the volume is going to go up, and vice versa. Okay, so we can set them equal to each other if we have a constant. And for us, that constant is density. So G times V. I guess I could just point it to the writing here rather than writing it down. But I remember it better when I write it, right? So the mass is equal to the density times the volume. So that D represents a constant. Density is a constant. So the density is never going to change for like a metal, for a particular metal, right? So for iron, the density is always going to be the same. The density for aluminum is going to be different than iron, but regardless of how much of aluminum I have, the density is always going to be the same. You guys can understand that?
Yeah.
Okay. So density is going to equal mass over volume. Simple. Where M, again, is mass, and V is volume. Okay. The most common units that we express density in is grams per milliliter. Is grams per milliliter or grams per cubic centimeter, okay? And that's typically if we're working with densities that are liquids or solids. When we get into gases, we're going to be doing grams per liter, okay? Because the numbers are so drastically different. I'll show you a table here in a second. Okay, so a couple things that I should tell you. Density is dependent on temperature. And that kind of makes sense, right? Because if you have the density of ice, it's going to be different than the density of water, right? So does ice float in water or does ice sink in water?
Float.
Float. Why?
Because the density is less than the water.
The density of ice is less than the density of water?
Yeah. Or
Okay.
yeah. I think so.
Okay. Piece of cake. Simple. Right? And you can visualize that, right? You're thinking about that cocktail you were having last night and your ice cubes are floating on top, right?
And my orange juice.
In your orange juice. You put ice cubes in your orange juice?
Yeah. It's not cold.
Oh,
I like
it's
it
not cold?
icy. I like it real cold.
Okay. Okay, and this is just basically showing you that, right? So we have the ice, and then we have water. The density of ice is less than water. Kind of for two reasons. One is because how it's organized and everything like that. It actually traps air molecules in between, so they're taking up that space. so it's not as heavy, okay? Where in the case if we were looking at the density of iron and we put that in water, what's going to happen?
It's gonna sink.
It's going to sink. So like an iron weight drops to the bottom, right? Okay, so here's an example. Again, ice and water. So if we have frozen amount of alcohol, we freeze ethanol completely, and we dropped it into ethanol. Well, it sinks to the bottom because the solid is more dense than the liquid, where ice is different. And that has to do with electrostatic forces, particularly hydrogen bonding, and we'll talk about that later to kind of keep you interested. Okay, so these are the different densities of different things. Helium gas, right? And these units are in grams per cubic centimeter or grams per milliliter. So we know that 1 cubic centimeter is equal to 1 milliliter. Okay, so, and this is at 20 degrees Celsius, which is about room temperature, and 1 atmosphere, which is the normal atmosphere that we exist in. Okay, so helium gas, very, very small density. Air, very small density. Hence, that's why it's in the air, right? Lumber. So if we have pine, 0.5. If we have maple, 0.6. If we have oak, 0.8. So if I throw a piece of wood in a lake, what happens to that piece of wood? Does it sink or does it float down the river?
It floats down the river.
It floats down the river, right? And that kind of makes sense. Otherwise, if we got a boat, it would sink to the bottom, right?
Yeah, that makes sense.
Okay.
Yes.
So we know that the density of wood is less than water. Now, a piece of glass. If I throw a bottle of glass or a broken piece of glass into the river, what happens?
It sinks.
It sinks, right? Have you guys ever been out in the river and you stepped on a piece of glass and you're like, God damn it, all bleeding and everything like that? I guess not. Do you guys even go out to the river?
No.
Yeah.
No?
Sometimes.
Love going to the river.
Oh, ocean, not the river.
What was that? You would go to the ocean, not the river? Yeah. Well, you can step on a piece of glass in the ocean as well, too. So.
To a
Okay.
river, but I've never been in one.
You've never been in a river?
No, just near it.
Near it? Ah, it's great. You got to try it once. Especially in this area, there's a couple of rivers, you know. Okay, so here, these are all different densities, right? And as you can see, you know, the different metals, they get pretty heavy compared to water, right? So 7.8 for iron, lead, 11.4, mercury, 13.6, gold, 19.3. So in all those cases, we'd expect those to all sink to the bottom, right? Okay, so knowing what you guys know, can you guys help me out with this problem? The question says, the mass of a 50.00 milliliter sample of methanol is 39.59 grams. Determine the density of methanol. So what am I going to do?
Mass divided by volume.
Mass divided by volume. Okay, so what is our mass?
50.00.
39.59 grams.
39.59 grams. And our volume is
50 milliliters.
but we want to make sure that we put our decimal point and our zeros because that's going to help us with our significant figures, right?
Yes. I forgot to put that.
Okay. So what do you guys get? Pull up my calculator.
0.7918.
And my units would be grams per milliliter. Piece of cake?
Yeah.
So let's make it a little more challenging. The density of a certain machine oil is 0.910 grams per milliliter. Find the volume occupied by 196 grams of that oil. Okay, so what am I going to do? What are my givens?
Um, 95 grams per milliliter would be the density. And then it would be 196 grams on top and X on the bottom.
Okay. So you're saying 0.91 grams is the density. Is that what you're saying?
Yeah, well, yeah, it says it's the density, so.
Okay. So we can sit there and do our equation and plug in our values and then solve for our unknown. So in this case, we have 0.910 grams per milliliter. Is equal to our mass, 196 grams, and then we're solving for our volume. Okay, so this is one way that we could actually go about it. The other way that we could do it is we can go with what we've been doing so far. We know that this serves as an equivalency, right? 0.910 grams per 1 milliliter, right? That's an equivalency. We know that we're given 196 grams. So I could actually start with 196 grams. I know I want to get my volume and use my equivalency. Am I going to put the milliliters on top or am I going to put the milliliters on bottom?
Bottom.
On the bottom? Well, we'll do it just for the hell of it, just to see, right? If I put my milliliters on the bottom, I have 1 milliliter on the bottom. I have 0.910 grams on top. Do my grams cancel out? Is grams times grams equal 1?
No.
No. So am I going to put my milliliters on the bottom or am I going to put the milliliters on top?
On the top, Dr.
On the top. So then I have 0.910 0.910 grams on the bottom. So then now gram crosses out with gram. So I get rid of that unit. And then I'm just left with milliliters. So what do you guys get? And how many sig figs should I have?
Like 272.
You got 272? That seems like a little bit much. So 196 divided by 0.910.
I got 215.
And so how many sig figs should I have for my answer? Because in theory, it's 215.38615
8, 4.
milliliters. How many sig figs should I have?
What determines the amount of sig figs?
So the things that we went over about a week ago or at the beginning of the week. So
Right.
how many whole numbers do I have? I mean, or non-zero numbers do I have in this number right here?
3.
3. So this number here is considered to be an equivalency. All equivalencies, we don't take into account for sig figs. So you kind of ignore that. So the number that I'm starting with has 3 sig figs. Then how many sig figs should I have?
3.
Now, if I was multiplying two numbers or dividing two numbers, right, just like I said in your notes, then you go with the one that has the least number of sig figs, right? So if we have to multiply this by some other number that wasn't an equivalency, right, then in that case, we're going to sit there and use those numbers. So if it was 1, then we'd have 1 sig fig. If it was 2, then we'd have 2 sig figs. If it was 8, we'd use 3 because this one has 3 sig figs, right? The one who's ever smallest. Okay, multiplication, division, the smallest one, right? Addition, subtraction, the one that has the biggest number with the most uncertainty. Okay? So look over those notes because I will dock you for sig fig and units. Okay. Simple so far?
Yes.
Okay, so important things, really important things to remember, right? I always start with what's given to me when I'm trying to solve the problem. What's given to me, right? That's a good place to start. If I have an equivalency, I know something over something, usually an equivalent, right? So I know I can use that to actually get started. So start with what's given and then use your equivalency, okay? And then see the units that you want, right? You need to know your units. Volume, what are the units for volume? What are the different units for volume? Is grams a unit for volume?
No.
No. Is milliliters a unit for volume?
Yes.
Is liters a unit for volume?
Yes.
Yes.
Is meters a unit for volume?
No.
Is
That's
cubic
fine.
meters a unit for volume?
No.
Yes.
Yes, it is.
Oh.
Cubic meters is, right? The cube, the volume of a cube. How do you calculate the
Cube.
volume of a cube? Right? Okay, so think about the problems. Don't make it harder for yourself. Don't overthink the problem. Just think about it and think about what you're given, okay? And learn what units represents what you're looking at. Are you looking at mass? Are you looking at volume? Are you looking at distance? Okay? Are there any questions? Okay, so we're going to be talking about Dalton. So you guys are familiar with Dalton. You've heard of Dalton before. A lot of the things that we're associating Dalton with is biology. But Dalton also did quite a bit of work in chemistry. So one of Dalton's laws, or work that Dalton did, was Dalton's atomic theory, right? And so he basically had this theorem that he had worked on, and he was saying, okay, so each element is made up of individual particles called atoms. And then he says atoms are indivisible, meaning that atoms can't be broken up into anything, okay? And then he said all atoms of one element are identical. They look exactly alike. They are exactly alike, okay? The other thing he said was that atoms of one element are different from atoms of another element. So two different elements aren't going to have the same atom. They're not going to be the same. They're going to be different from each other. And then the last thing he said was atoms of one element combined atoms of one element combined with another element form chemical compounds. And we already know that one, right? So, because you guys we've been talking about it. Okay? So I want you guys to sit there during this lecture, think about this, think about these different points that he said, and then I want you to see if it stays true. Okay? And then we'll come back to it, okay? So this is just basically giving you the images of all of those theorems, of his atomic theorems. Again, very first one, an atom is made up of an element is made up of atoms, and all atoms of a given element are identical. Atoms, they can't be created or destroyed, meaning you can't cut them up into little pieces, right? Okay, and then he says all atoms of a given element have the same properties, so they weigh the same, you know, they behave the same, okay? And then, but atoms of different elements are going to weigh different. And then lastly, I can combine atoms together, but the ratio that I combine them are, it could make two different elements. Like, so for instance, we have this blue ball and the red ball. So here, this compound has two blue balls and one red ball, where this compound has one red ball and one blue ball. That ratio, regardless of how much I have, that 1-to-1 ratio is always going to be the same. Or that 2-to-1 ratio is always going to be the same for that compound. Okay, so let's go and we'll start with that last one. Okay, so the law of multiple proportions, or it's also called the law of definite composition, or the law of definite proportions. So it basically says that, and I'll say it two different ways. So if I have one carbon atom and one oxygen atom, right? That's carbon monoxide. That compound is carbon monoxide. Regardless of how much carbon monoxide I have, the ratio of those atoms to each other is always going to be 1-to-1. Okay? So where carbon dioxide has 2 oxygen to 1 carbon. Now, carbon monoxide and carbon dioxide are two different compounds. They don't behave the same way. They have different effects. Okay? So carbon dioxide is always going to have a 1 carbon to 2 oxygen ratio. Okay, and we can also do this in terms of mass. And it's first, when it was first talked about, it was talked about in terms of mass instead of just the atom itself. Okay, so what is the mass of carbon? Atomic mass of carbon? Anybody there? Knock, knock. Am I talking to myself? Who has a periodic
Where is the
table?
periodic table, huh?
Yeah, periodic table. You should always have one handy.
I need to print that out.
What was that?
I need to print one out. I need to print all this stuff out. 'Cause
Always
my-
have a handy dandy periodic table.
Yeah, because my Wi-Fi is not working. I usually just look it up on my laptop, but
Yeah,
I bet it'd be better just to have it on paper.
yes, it is. Let me pull up a P table. Hold on.
Is it 12?
That's right. It's 12. Okay. What is the, it's, well, 12.0111. Okay. What about oxygen?
15.
15.9999 is 15?
It's
16.
15.99.
Yeah, 15.99, right? Or 16, right? So it's 12 to roughly 16, right? We could say that. So one carbon,
Yes.
12, one oxygen, 16. So the ratio is going to be 12 to 16. So regardless of how much carbon dioxide or carbon monoxide I have, it's always going to have a ratio of 12 to 16. Okay, so if I have a ton of it, if I add up all of the carbons and all of the oxygens, it's always going to have that ratio. It's not going to change. Okay, so that's what that's saying. Okay. Okay, so now what actually happened was that we found that there were particles that were smaller than the atom, or the atoms were made up of subatomic particles. There were 3 particles. We've talked about these before. We have the electrons. What are the other 2?
Proton and neutron.
Protons and neutrons. What is the charge on electrons?
Negative.
Negative. So electrons has a negative value assigned to it. So we give it a negative charge. This is the symbol that we use. And the other thing that I want to say is that a proton is 1,837th of a proton, because we know that the hydrogen atom is composed of, or I should say, the hydrogen nucleus only has a proton in it. It doesn't have a neutron in it. Why doesn't it have a neutron in it? How can we be sure of that? How did I figure that the hydrogen atom only has a proton in it? So what is the atomic number for hydrogen?
Isn't it 1?
Okay, atomic number is 1, right? And what is the mass number?
It's also 1.
Okay. Okay, and if I have my number of neutrons, it's going to equal mass number minus my atomic number. What is my mass number? You said it was what?
1.
Oh, it was 1.
It was 1. Okay, so 1 minus 1?
0. Is 0.
So that means that there are 0 neutrons in the nucleus, right? So the nucleus is going to be composed of protons and neutrons, but hydrogen doesn't have any neutrons in it. Okay, so in other words, I'm saying that the electron is kind of like a speck of dust, right? It's like the equivalent of a speck of dust on me. So I weigh 220 pounds. If I put one little speck of sand on my shoulder, is my weight going to change?
No.
No, it's going to be so little compared to my mass, right? That is not going to change. I get on my scale, I'm still going to weigh 220 pounds, right? So that's exactly what, in the case of the electron. The electron is so light, right, that it doesn't affect the weight. The weight is only going to be affected by the number of protons and the number of neutrons, okay? So that's the weight of the atom. It's the number of protons and the number of neutrons. Okay, so lastly, electrons were basically discovered by J.J. Thomson, right? And so J.J., he was sitting there in the lab and everything like that, and he says, you know what? There are these electrons, right? And he's like, so there are these positive and these negative charges. And so they kind of, I bet you it's just kind of like they make this pudding, right? And plum pudding. I never known what plum pudding was before. I had to actually look it up, right? And so plum pudding is kind of like a bread pudding, and they use plums to make it. So they put the plum in there and they make a little dough and everything like that. And they just kind of throw everything together and it's all mixed up, right? And so that's what he's saying. He's like, it's just like that, where you have positive and negative charges embedded through the entire gel type of surface, right? And but that's not the case, right? And one reason that we know that's not the case is because this guy named Rutherford. Rutherford came in and he's like, okay, so I'm going to do this really cool experiment. I'm going to shoot these alpha particles. Alpha particles are positively charged particles, and I'm going to shoot it at this gold foil, right? And he's like, you know, if I'm right, it'll all shoot right through, right? And then we're not going to get anything crazy, okay? And then he's like, you know, that's basically my hypothesis, right? So when he did it, he was like, he shot it through, and he's like, you know, I had ones that went straight through with no problem, but there was deflection, right? So if it was all kind of embedded really randomly, right, I would have this constant deflection everywhere, right? Because these particles would bounce off of the positive and negative charge. But he noticed there was like a pattern towards his deflection. He also noticed that there were particles that were going straight through, right? So it wasn't totally randomly everywhere, but there were ones that were able to go straight through. If you kind of take a look at it, this is basically what's happening. So that foil particle has some type of order associated, for one thing. The other thing is, what happens if you have two positive things coming together? If I put two positive charges together, what happens?
They repel each other.
They repel each other, right? And so they're gonna be deflected. And so he saw that deflection. So that meant that we had something in the center that was positive outside of that those negative charges. So basically, that meant that there was that nucleus. So the atom has a nucleus that has a positive charge in the middle, and the electrons, the negative part of it, is going to be occupied in the outer space. And that's kind of shown here in this little diagram, okay? Okay, so the nucleus is the majority of the mass, right? It's the mass of the atom. Now, the volume of the atom is going to be occupied by the electrons. So let me show you what it looks like. So that's your nucleus. Your nucleus is going to be composed of protons and neutrons. Now, the size of a normal nucleus, or the average nucleus, is 10 to the minus 14 meters. The average size of an atom is 10 to the minus 10 meters, okay, in terms of diameter. Okay, so that means this guy, the nucleus, is 10,000 times smaller than the atom. Okay, so that means that the majority of the space is being occupied by electrons. So what's happening is that you have your nucleus in the middle, and you have these electrons that are around it, circling it, right? Orbiting it. You know, I shouldn't say circling it, because I'm going to throw screw you up later on. But it's orbiting the nucleus. So you have your nucleus in the middle, and then your electrons are orbiting. And that the electrons are kind of like a cloud, right? So it's just a cloud orbiting the nucleus, okay? So that just basically proves that there's this positive charge in the middle, and we know that that positive charge comes from protons. Protons are positively charged, and these are the symbols that we typically will use for it. So we'll say P plus, or just P for protons, lowercase p. Neutrons are neutrally charged, right? And a neutron and a proton, they weigh about the same. So that's how we add them both together. They're going to equal the mass of the atom, okay? So we've talked about the electrons and its mass. So let's talk about isotopes. Okay, an isotope is an atom. It's two or more atoms of the same element that have different masses. Okay, so two or more atoms of the same element that have different masses. Okay, so what do I mean by that? How can they be different masses? How can they have different masses? Okay, so earlier, and I said it last week, and you probably banked it up and said, oh yeah, he said something, but I don't remember what it is. Earlier I said the atomic number defines the element, right? Did I say that? Do you guys remember me saying that? Yeah, no, maybe?
Maybe.
Yes. Yeah.
Yes. Okay, so just to remind you, the atomic number defines the element. Okay, so if the atomic number defines the element, that's also, the atomic number is also the number of protons. So that means that protons define that element. So carbon is always going to have how many protons?
12.
Nope, not 12.
6.
6. So its atomic number is at the top of the periodic table, typically written right up top. That's the atomic number. It's going to have 6, right? Its mass, if you look at the bottom for that one, that particular isotope is 12, roughly 12. That's how much it weighs, okay? So don't mix up its atomic number and its atomic mass, okay? So now what I'm telling you is that I could have two atoms that have the same number of protons. They're both going to be carbon, but they're going to weigh differently. Okay, so just a quick refresher, and I didn't tell you this. Often we will use Z to represent the atomic number. Okay, and then we'll use A to represent the atomic mass. So if you say A equals Z plus N, N being the number of neutrons, then that's going to give you your mass number or your atomic mass, roughly. Okay, so let's get to the nitty gritty. Then we'll do a quick example, and then we'll have to stop here. Okay, so the way that we write isotopes, right, to let us know that they're different in mass, is we use a superscript. So we use the number on the left-hand side, just at the top of the symbol for the element. So this tells me here that the atomic mass, or its mass number, is 12. This here tells me the number of protons, or my atomic number. Okay, so that's what it's showing you here. Okay, SY means symbol. Okay, so we know that the atomic mass, or the mass number, right? The mass number is the whole number of the atomic mass, is just the sum of protons plus neutrons. Okay, so carbon 12, how many protons does carbon 12 have?
6.
Okay. How many neutrons does carbon-12 have?
Also 6.
Okay. Okay, how many electrons does carbon-12 have?
6.
Okay, what about how many protons does carbon-13 have?
Protons, 6.
6. How many neutrons does carbon-13 have?
7.
7.
And how many electrons?
6.
Piece of cake?
I had a question.
Yep.
That's good.
So for the atomic mass, how it says 13, could the 7 and 6 flip, or it's always 6 and 7? Like,
Okay,
'cause
what
it's,
do we say about what defines carbon? What makes carbon carbon?
The atomic number?
The atomic number. And the atomic number is always going to equal,
6.
in this case, it's always going to equal 6. And it also is always going to equal the number of
the protons.
Elements?
Or protons.
the number of protons, right? It's going to equal the number of protons. Okay, elements is what we're talking about. We're talking about carbon. Carbon is the element, right? Okay, so
Oh, I see it. I see it.
do you understand? So
Yeah.
protons is always going to be 6, right, for carbon. If we're talking about nitrogen, that's different, right? But that's a different element, right?
Right.
Okay, so do you guys kind of get this? Yay, nay?
Yeah.
Yep.
Okay. Okay, so we're actually going to stop here. One place shorter than we stopped the other, and we'll bring it back up. So I want you guys to start thinking about it a little bit more and, you know, kind of keep track of it. Oh, wait. Before we do that, though. So let's talk about Newton's law, right? So which parts of Newton's law were BS? Now, don't you guys all yell at me once. You're talking too much. Should we go back to Newton's law to see?
Yeah, that's what
Yes.
Okay. Let's go to the other one. It's a little more detailed. Okay. What about this first one? It says, each element is made up of individual particles called atoms.
That's correct.
Okay. Atoms are indivisible, meaning they
Correct.
can't be broken down. It's correct?
False.
False. Why is it false?
That's how nukes were made, by breaking
Because of
atoms.
the
Because they
can't
protons,
be
broken up.
electrons, neutrons.
That's right, because we have subatomic particles. We have protons, neutrons, and electrons. Okay. The next one. All atoms of an element are identical in every respect.
False.
false.
False. Why?
Because the atoms have different charges.
Because they have different charges. So they can't have different charges. We haven't got to that part, but yeah, you're correct. That's true. But not necessarily that reason, but there's another example.
Masses.
They're masses. Yes, so I could have the same atom, carbon-12, or I could have carbon-13, and they weigh differently, right? So So for both of those, yeah. Okay. What about the next one? Atoms of one element are different from atoms of another element.
True.
True.
That's true, right? And that still remains the same, okay? That's going to be true. Atoms of one element combined with another atoms of another element will form chemical compound.
True.
True.
Okay? So there were only two of them that were wrong, right? So they didn't do too bad, you know? Okay? So, questions?
So how you got that 7 was because you said that the atomic number always equal the number of protons. So then that's when we get it from the neutrons.
Yes. So you subtract the mass number, right? You mass number subtracted by the number of protons is going to give you your number of neutrons.
Oh, okay. Thank you.
No problem. Oops. Let me go back to that slide. Okay, yeah. So this is the equation, right? And we just modify the equation. So we have mass number is A minus Z is going to equal. Okay, any other questions? Okay, so this is going to be our stopping point. Remind me.